Hi everyone. Welcome to this talk on trusted execution environment on ESP32-C6. So here is the agenda of this talk. Introduction to figure out why trusted execution environment is required and what it is. Trusted execution environment on ESP chip, ESP TEE architectures, a little bit on internals of ESP TEE, and some of the use cases. So before we start, here is a brief introduction. Myself, Sachin Billore, and with me, my colleague Loki Khasi. We are part of the security team at Expressive Systems. We are responsible for building and maintaining the security features for ESP IDF framework. We are also responsible for basic building blocks, which goes into developing the security features. For example, crypto peripherals, some proprietary security IPs, and other system security related stuff. So, okay. So let's start with introduction to find out the answer why trusted execution environment is required for a device and what is trusted execution environment. Okay. So for any embedded device, security countermeasures are generally defined by the threat modeling of that device. And so let's start with a abstract threat modeling for an embedded device to figure out the answer why trusted execution environment is required for a device. So a device generally hosts various kind of data, which maybe belongs to various stakeholders of the device. Uh, and some of these data could be security sensitive and needs some confidentiality protection. So these data generally we term as security sensitive assets here, and these are generally the interest of attackers on the device. Some of the example of these security sensitive assets are as shown here, but not limited to these: cryptographic keys, personal data, third-party IPs if they are also integrated into the device, and OEM has some obligations to protect these IPs. So confidentiality protection for these data could be provided by encryption when they are at the rest. But when device are using these assets, they are generally present in the internal SRAM, internal memory, or CPU context in the plain text. And there they may be subjected to some threats. Uh, some of the possible threats as we are listed here, but not limited to these, are malicious code, which may be part of device software already, some form of runtime tampering, or some exploitation of vulnerabilities which are not fixed in the device software. Threat to these assets also depends on the kind of attacker, their motivations, their capabilities. So we also consider here local agents uh, who have physical access to the device, or remote agents who have actually the access to the device, where access to the device network. So here is a simple device threat model we have, which help us to identify the security sensitive assets on the device and potential threat to those assets. So one of the mitigation strategy to protect assets from these potential threats could be uh, to focus on these identified security sensitive assets only instead of entire device, because protecting entire device could be more complicated, and probably attackers interest only on these security sensitive assets. In other way, we have actually, with identification of these security sensitive assets, identified a reduced attack surface where generally attackers are interested in. So how we will protect this reduced attack surface? One of the strategies is to isolate these reduced attack surface from rest of the system. Not only these assets, but all related resources which actually involve in dealing with these assets. For example, a piece of software and hardware. So security by isolation is one such mechanism which actually provide the isolation to these security sensitive assets. It not only provide confidentiality to these assets, but also ensures the integrity and authenticity of this execution environment. Here, one point to note is this isolation by security mechanism does not focus on hardware attack, both invasive or non-invasive hardware attack, for example, fault injection or side channel attack. We may need another set of countermeasures to protect against this kind of hardware attacks. So now we understand what is security by isolation and why it is required for an embedded device. So let's formally define the trusted execution environment, which is nothing but isolation mechanism defined by hardware and implemented by software. So trusted execution environment is an isolation mechanism which actually separate virtual execution environment on the same set of hardware where actually your traditional execution environment is host. It helps to isolate all hardware and software security sensitive assets and host them, protect them from the rest of the traditional execution environment. Since it is hosting all security sensitive resources, this term comes a trusted execution environment. And rest of the execution environment which hold traditional software stack is called rich execution environment. Trusted execution environment also provide a well-defined and clear interface to rich execution environment. During the course of its execution, whenever rich execution environment processing depends on this security sensitive assets, it calls into trusted execution environment using this interface. Trusted execution environment perform operation on these security sensitive assets and return the output of those operations. So in this way, rich execution environment actually avail the service of trusted execution environment without directly accessing these assets. And trusted execution environment is protect the confidentiality of these assets from the rich execution environment. So we have defined what is trusted execution environment. So let's understand it a little bit more using some real world example. So as earlier, we identified one security sensitive assets, which is cryptographic key. We also consider related resources. Here, a piece of code, which is secure application, which use this key in its operation, and also probable hardware, like crypto hardware, where these operations may be offloaded. So these security sensitive assets, cryptographic key and related resources, software and hardware, are actually hosted by the TEE and protected by TEE from the rich execution environment. This key could be generated on device under the protection of TEE, or this key could be provisioned in the device under the secure provisioning mechanism during the manufacturing of this device. Now, this device is hosting and protecting cryptographic key securely from the rest of the system. Uh, gives us many use cases. Some of the use cases we have listed here. For example, challenge response protocol, which is actually the basis of many other security features. For example, device attestation, which is used in recently launched Meta protocol. Managing the debug ports securely on the production devices. Uh, Secure keys also used, as we know, in various communication protocols where mutual authentication and encryption of the communication is required. So apart from these use cases, we should notice two more points here. One is as we defined in earlier slide, the T isolation mechanism is actually defined by hardware, and a hardware is not modifiable. Once it is configured, it cannot be modified so easily. So we can rely this trusted execution environment isolation mechanism, which is rooted whose trust is rooted into the hardware. So hardware is kind of provide root of trust for this TE isolation mechanism. At the same time, as we have seen this in these use cases, uh, these security features are actually leveraging that. Can you please? Yeah. These security features actually leveraging this hardware root of trust isolation mechanism and implementing different security features, which are actually based on the device requirement. So here we actually leverage the best of both world, hardware rigidity, which provide the hardware root of trust, not modifiable so easily in the device, and the flexibility of the software implementation, which help us to define different security features protected by this isolation mechanism. Another point to note here is that cryptographic key is at the core of all these security features we were discussing here. And this cryptographic key is hosted and protected by trusted execution environment. In the absence of trusted execution environment, also we can host these keys in the device securely, but generally that use some costly hardware mechanisms like OTP, which doesn't provide that kind of flexibility which software implementation provides. In case we have to revoke the key, we have to use another bank of OTP, which is again costly for a device. But in software implementation, you can easily revoke or replace that key using some secure protocols. So now we understand why trusted execution environment is required, what it is, its benefits for the device. Now let's dive into the trusted execution implementation on the ESP chip. So we start with this uh, architecture of the trust ESP TEE on the ESP chips. So as we mentioned earlier, the trusted execution environment is a parallel execution environment which hosts on the same set of hardware parallel to rich execution environment. And the isolation is established by the hardware mechanisms. So here this vertical line is actually representing the isolation between rich execution environment and trusted execution environment. uh, and a horizontal line is actually the boundary between software and hardware. You can see here, bottom right hand side, immutable root of trust. This is actually the secure hardware which are part of the trusted execution environment, and actually provide the mechanism to establish the isolation in the system between RE and TE. And since it is rooted in the hardware, these mechanisms cannot be modified by any entity in the system. On top of this immutable root of trust, which is represented by this secure hardware, we have ESP TEE firmware, which is actually extend this root of trust, leverage the trust of this immutable root of trust, and form the updatable root of trust. This is a software implementation, so it could be updated if required. And it provides various mechanisms, and actually it use the hardware mechanism during the boot to establish this isolation between RE and TE. So system actually boots from the immutable root of trust, on which updatable root of trust ESP TEE executes and initialize the TE, as well as establish the isolation between RE and TE. And on TE side, on top of the stack, we have secure services, which is actually depends on the use cases and developed on top of the ESP TEE firmware using its provided API. So we saw the abstract view of the ESP TEE. Let's understand how it is relies on the chip, on the ESP chip. So ESP TEE is designed for the ESP SoCs based on the RISC-V architecture. We use RISC-V primitive security features to implement the ESP TEE. So these are the basic building blocks and requirement from an RISC-V SoCs to support the ESP TEE. These are AM and U mode privilege mode, where AM mode is higher privilege and host the ESP TEE firmware. U mode is a lower privilege mode, which actually hosts the ESP IDF now. So impact of bringing ESP TEE on the system, on the device, you can see here in this picture. ESP IDF, which currently execute on the machine mode, is now shifted to lower privilege mode, user mode. In machine mode, we host the ESP TEE with higher privilege. We use another primitives, memory protection primitives from the RISC-V architecture, which is PMP and PMA, physical memory protection and physical memory attributes, which are configured to realize the isolation between TE and RE. We also use U and M mode environmental call, or eCall, which we call in short, which is used to switch between the word RE and TE. We also use proprietary peripheral APM, access permission management, which actually complement and extend the capability of RISC-V primitive PMP and PMA to further establish the isolation between ESP TEE and RE. Along with this, the trusted and untrusted hardwares are placed into their respective world with the help of this isolation mechanisms configured in the hardware. So this is actually the immutable root of trust, which we just discussed, hardware primitives and hardware mechanisms, which is configured to realize the isolation. Now we talk about updatable root of trust, which are basically ESP TEE and its internal components. So once device boot and ESP TEE actually comes into the picture in initial stage of the boot, it configure the hardware to realize this isolation. It hosts some other components which we will discuss later part of this talk. As part of this ESP TEE firmware, important point to note here is it provide TEE API, which actually RE application use to call into TEE secure services whenever they need the service of whenever they need to call into the secure service. So here we can see uh, secure service during its execution time whenever they need a service from the secure from the TEE world. They use this TEE provided API, which internally actually execute the eCall exception and switch to the TEE firmware, which is routed to secure service. And after performing the execution, it returns back to the RE applications. So as we talk about, we use some primitives from the RISC-V architecture and proprietary hardware uh, to realize isolation between TE and RE. So this is here we are talking about how PNP, PMA, and APM is used to establish the isolation between TE and RE. This picture actually shows how PMP, APM, and PMA actually placed on the bus uh, on the CPU access bus to different memory addresses. The access generated by CPU actually filter from the APM if it is directed to these memory ranges, and if not, this access is actually goes to APM, another filter, which actually controls these ranges of the CPU address space. So by configuring these primitives and APM peripheral, resource isolations are achieved. And this configuration actually locked once it is performed, they cannot be modified by any entity, even in the higher privilege mode TE. So as part of this isolation, we established the isolation in the SRAM, where actually ESP IDF and ESP TEE loads at the runtime. So as we can see here, internal SRAM initial addresses are reserved for the ESP TEE, and lower addresses are open for ESP IDF to load and execute. These partitions are also again internally partitioned to configure the access for text and data sections. Text section with read and execute, data section with read and write. And similar configurations are performed for the REE. And this isolation boundary actually doesn't allow REE to access the TEE protected region for ESP. Since in a resource constraint device, not entire code or data is loaded into the internal SRAM, some non-critical code and data remains in the external flash, and we use as a XIP to execute this code. External flash is also partitioned between ESP and REE. So here we are showing partition for external flash, where initial range of the flash is actually controlled or protected for the ESP, which hosts the ESP firmware, partition table, bootloader, and secure storage governed by or protected by ESP. Uh, During establishing the isolation, peripherals are also isolated. Secure peripherals are also isolated in the TE, which is actually all crypto peripherals, interrupt controller, eFuse, and APM. So this is all about ESP and its architecture. Now let's dive into its internals and use cases, for which I request Lokik to take over.
Okay, so thank you, Sachin, for the wonderful explanation. Hello all, I'm Loke Kase, and I've been working for SPSIF as an embedded software engineer for the past 3 years, and I'm a part of the security team. So let us now continue. We left off and discuss some of the internals of ESP TEE, and let's start with the secure services. So first, we have the secure service call table, where all the secure services have been defined as an index list, and this list has been shared with the RE. The RE uses the appropriate ID from this table to request the necessary services. The diagram on the right explains the flow of a typical service, secure service call. So when the application requests a service, an equal instruction, that is environment call, is triggered, which lands us in the TE exception handler. In the handler, we save the RE context, we push to the TE stack and disable interrupt delegation so that we get notifications for all interrupts while we are servicing the request. Next, we have the secure service dispatcher. Now, this passes the input arguments and passes the control to the appropriate service for execution. Once execution completes, we restore the RE stack, enable interrupt delegation, and switch back to the RE at the interrupted point where using the emirate instruction. There are the ESP TEE framework offers two types of secure services. First, there are the ESP IDF secure services, which provide essential functionalities which are essential for a system to function. These include the crypto API, the AES and SHA peripheral, the interrupt matrix, and the EFUs. Second, there are the custom secure services. These are optional secure services which can be configured as needed depending on the user application. Secure storage, secure OTA, and attestation are some of the default ones which are included with the ESP TEE framework, and users can also define their own secure services as required. So let us now see how interrupts are handled with TE. In the ESP TEE framework, the TE and the RE maintain separate vector tables. The interrupt sources also have been divided within these two environments. So secure interrupt sources like the SHA peripheral, the ES peripheral, and the APM are protected from the RE. That means they would always be handled in the TE itself. While interrupt sources like the FreeRTOS stack or Wi-Fi, ESP timer are managed by the RE. When the CPU is operating in the RE mode, all these interrupts for RE would be handled in RE itself as they're delegated. So now, since we have two environments and each with its own interrupt sources, we have about 4 interpreted scenarios that we need to handle. So these scenarios have been illustrated in the diagram. Noted careful consideration has been given to ensure that minimal interrupt service delay is there for all the scenarios. Service calls do not delay or block any interrupts, as any delay could lead to unwanted consequences like delayed task scheduling or poor Wi-Fi packet delivery. So now coming to the boot sequence, with ESP TEE enabled, the boot sequence differs a little bit from what we see in a typical ESP IDF application. After the reset, the boot ROM loads a second stage bootloader. This bootloader verifies the TE as well as the RE application images. Now, instead of jumping to the user application, the sequence jumps to the TE first, which performs all the secure system initializations for the memory, interrupts, and peripherals. After that, the control passes to the user application for execution. So now, as we have seen the architecture and the internals as well, now we can jump on to the use cases and the practical applications of what the ESP TEE framework has to offer. So first of all, we have the secure storage. So the TEE secure storage service provides persistent storage for securely holding sensitive data such as cryptographic keys, cloud credentials, and or the other general purpose information that a user might have. It utilizes a dedicated external flash partition, and the data stored in the storage is encrypted using the AES GCM scheme with a 256-bit key, which is device-specific key, which is programmed in the eFuse itself. Note that the TEE ensures the confidentiality and the integrity of the data. Any attempt to access the data or the key from the RE results in a system fault. So currently, the secure storage supports storing ECDSA key pairs with about 14 slots, and also provides an interface to the RE for securely signing messages in the TE using the key material which is already stored in the secure storage. The signing algorithm that is supported currently is the ECDSA SCCP 256R1 curve, and the digest is the SAR256. Now, the next use case is the over-the-air updates for TEE, which is practically very essential for all devices that are going to be deployed in the field. So TEE OTA requires configuring the device's partition table with 2 OTA application partitions and 1 TEE OTA data partition. The diagram on the left illustrates the TEE OTA process. The RE app is responsible for downloading the TEE OTA updates because the TEE app is itself is minimal. Now, however, since RE does not have permission to write directly to the TEE flash region, it issues the appropriate service call to write the new TEE firmware to the flash. Once the update is complete, the TEE verifies the update and reboots. Now, TEOT update mechanism also supports app rollback. So during the TEE startup initialization routine, it performs a self-test, and if the self-test passes, uh, it moves on with a new image, and if the self-test fails, it rollbacks to the previous image. Uh, TEOT updates are also compatible with the secure boot scheme that we have in ESP IDF. The TEE image needs to be signed with the same key as that of the bootloader as well and the RE application. So now moving on with the next circle service, which is attestation. So attestation is a process used by a device in the field to communicate evidence of its credentials and operational state to a remote relying party such as manufacturers and cloud service providers. And the information that is collected is structured into a token called entity attestation token, which is a cryptographically signed small data blob containing device information or claims defined in the JSON format. So some example of device claims would be device ID, which is MAC address, or the software version. In our case, it would be the ESP IDF version with which the application was compiled, or the hardware version, that is a chip revision on the ECO version. So in simpler words, you take a snapshot of the device's states and properties, structure it as a token, and send it to whoever needs to verify the device's state at any given point of time. The diagram shown illustrates a high-level overview of the attestation process. The relying party sends, which is the remote party, which I think manufacturer or cloud service providers is an example for that, sends an attestation request to the device's RE side. Now the RE forwards the request to the TEE's attestation service via the secure service call interface. The TEE generates and cryptographically signs the entity attestation token and sends back this evidence to the relying party. The attestation service, which I think in some cases relying party and the attestation service both can be the same, verifies this evidence and compares the claims that the token has with the reference values that the relying party already has. And based on this, it determines the device's trustworthiness and communicates the result back to the device. So the ESP TEE framework provides an interface to generate and return a token from the TEE. The EAT is signed using the 256-bit key CDSA key material from the TEE secure storage, as we already saw, and this slot number is given in the attestation request itself. The diagram on the right illustrates the information that is provided by the EAT. There are three major parts, which is the header, the claim data, and the signature block. The header contains the magic bytes and the signature algorithm that the token follows, and the secure storage slot ID. While the signature block consists of the public key corresponding with which the token was signed and the signature itself. The claim data is the major part which gives a lot of information on device's state. It includes the hardware version, the software version of the chip, and for all active firmware images, that is the bootloader, the TEE application, and the RE application, it provides the claims such as project and ESP IDF version, image digest, SHA-256, and it also has a field where it signifies whether the calculated digest and the one that is embedded in the image match or not. It also contains a public key, and then we have the ECDS signature in the end. So now we are done with the use cases. Now we would see how, when the firmware gets public, we would use it. So first, we would need to enable the TEK config option that we have and update the partition table with the TEE app and data partitions as required. Rest all remains the same from the RE point of view because TEE firmware generation and routing of service calls are handled by the build system itself. For example, take AES encryption. So user applications would call the API, some MBTLS API related to AES encryption like MBTLS AES encrypt. With ESP TEE enabled, it needs to be routed as a service call, but no changes are needed in the application itself as it has already been taken care by the framework. Thus, all secure services are in essential are ESP IDF compliant. Reference examples and detailed documentation will always obviously provided when the framework gets public. Now let us discuss some numbers regarding the performance and resource impact. So 64 kilobyte of SRAM and about 280 kilobyte external flash are reserved for the team. Do note that these numbers are configurable and depend on the use case. For example, if the attestation service is not required, the SRAM usage can be reduced. Or if TAOT is not required, then I think you can remove one of the TE app partitions that we have, and which can reduce the external flash requirement to about 128 KB. Each service call introduces a total overhead about 1100 CPU cycles, which is approximately 7 microseconds at the 160 megahertz frequency that the ESP32-C6 CPU operates. For all the interpreted scenarios, interrupt service delays are and overheads are minimal. So coming to the future work, the beta version for the ESP TEE framework will be releasing soon. It will be part of the ESP IDF itself and with its own set of examples and detailed documentation. Support for other RISC-V SoCs is in the planning phase. We are also exploring security certifications and regulatory compliance, such as the PSA level 2, which would guarantee that our SoCs are protected against scalable remote software attacks. Additionally, we are also working on optimizing the performance and resource impact so that it becomes easier for users to integrate this into their products. So that's it for today from our side. We hope that everyone enjoyed the talk. We'll follow up with a Q&A session. Thank you.